So the last presentation of today before the lightning talks, Yaliu on automatic classification through register messages. You have the floor.
Thank you, Mark. Hello everyone. My name is Yaliu. I come from the Network Security Research Lab of Qihoo 360. And my talk is about malware classification. This is the outline. Firstly, I will take some time on polymorphic malwares and current classification technologies. Secondly, I will talk about CNC protocol-based classification. Thirdly, I will show you our solution, including the definition of register message and the solution details. Next is elements and evaluation results. Then I will show you some pitfalls that exist in our solution. The final part is our conclusion. As you know, a great many of new samples are captured every day. This figure is borrowed from our Q1 Internet Security report. I would like to notice that the unit is 10,000. Our study shows that most of the new samples are just polymorphic variants of known malwares. They are created by the technologies of packing or code obfuscation. Malware classification is a technology that classify a large number of samples into a relative number of families. That simplifies the malware analysis and detection problem. Current classification is mainly based on the static sample signatures, such as the size, strings, or binary code snippets. It has false positive and false negative issues when dealing with modern polymorphic malwares, because the signature database update speed may not catch up with the malware growing speed. As you know, most modern malwares are distributed to build botnets. They can be used to make money by launching DDoS attacks, or spamming, or click fraud, or other bad things. It's proved effective that classifying botnets or malwares based on their CNC protocols. Such a classification is mainly based on the protocol message types, formats, or interactions. This means you need to know the detailed protocol specification. In most cases, you have to manually reverse the samples to get the detailed protocol specification. This causes a scalability issue. Before talking about our solution, I would like to show you our definition about the register message. It is the first message exchanged after a C and C session is established, and it must be sent by the bot. Sometimes it's also called login, hello, or call home. Its main usage is to tell the controller the bot's machine configuration, such as operating system version, CPU information, memory size, or net speed. It can also be used to report hard-coded information copied from sample for the bot mask to tracking the bot version. Many known botnets use this message in their protocol. Here are some examples. The first column is bot name. They are Daxel, Alconote, XR, DDS, China, Z, Mayday, and Doflo. Some run on Windows, some run on Linux, and a few run across both platforms. As you can see, all their register messages include the operating system and CPU information in their register messages, except for XR, DDoS, and Mayday. or include memory information in the register message. This is a detailed register definition for Elknot. This bot is also called Bill Gates. The right is a C language style structure. As you can see, this bot's register message has a binary format and have semantic strings inside. Okay, this is a register definition for the Doflu family. This bot is also called Mist Black. In most cases, it has this text format, as demonstrated by the following examples. There is a term in information theory called channel entropy. The wiki says entropy is a measurement of unpredictability of information content. Its value is calculated by this formula. And channel entropy can be used to measure how statistically similar two messages are. When used in register messages, small case xi stands for the unique message byte. Here are some example standard information about register messages. The first column is bot name. They are Kellyhouse, XR, DDS, Mayday, and Elknot. Except for the last one, they all have fixed length value. And different families have different entry ranges. But the value is very close inside the same family. And you can see there is so much information included in register message that we propose a new classification that is based on the similarities among registers in statistics and structure. We think our solution is extending C and C protocol-based classification, but we think it's more scalable because the register message is more easy to get than the whole protocol specification. This is our objectives. Our objective is to classify unlabeled samples based on the register messages. What we really do is to find out the number of register families and generate signatures for later identification. We will not tell you which cluster of registers are malicious and which are not. This is left for decision by human. And our system will not classify HTTP-based registers because there have existed good such a solution. And as you know, there is so much classification information in HTTP that we think it's better to classify them in a separate solution. This is our solution architecture. Firstly, the new samples are run in our sandbox. The network traces are saved. At the same time, we also download network trace from virustotal.org. Secondly, the network traces are input to the register profile. And after deduplicating and excluding HTTP requests, the unique registers are divided into two large TCP and UDP clusters. The result large clusters are input to a step called coarse-grained clustering. This step is to produce statistically similar clusters. And the result smaller clusters are input to a step called fine-grained clustering. This step produces structurally similar groups. In the final step, 3 types of signatures are generated. And the generated signature will be used to rescan all the input registers to exclude those successful classified ones. And the left register will be input for the next round of clustering and signature generation. The iteration will not stop until there is no new structurally similar groups are produced or no new signatures are generated. Register profiling. Basically, it's a process of passing PCAP files and creating the register structures. At the same time, it also set up such attributes for each register. They are length, entry value, binary or text format, and semantic strings. Here are two sample register profiles. The left one has binary format. Its length is 260. It has low entry value of 0.7, and it has 3 semantic strings. The right one is easy to understand. For consideration of time, I will not explain it in detail. Coarse-grained clustering. This step is used to group statistical registers. Basically, it's a step of k-means clustering on vectors of length and entry. We arrange this step is just to reduce the computation cost, because ON squares computation cost is needed if you attempt to directly find out structurally similar registers. Currently, you use a heuristic deduction procedure to find out the semantic strings. The frequent encodings of common semantic strings are concluded. Every semantic string has the following attributes. They are semantics, offset, and size. A length, it's common that a length field is used in message to indicate how many bytes the message has. We concluded the 3 types of semantics, as shown in the figure. The first is length value equals to length 3. The second is length value equals length 1 plus length 2. The third is length value equals to length 1 plus length 2 plus length 3. And the length field may have different field size. Currently, we consider 3 cases. And it may be placed in different byte order, host byte order or network byte order. Structure similarly. This step is also called fine-grained clustering. It is used to find the structure similar registers. 2 registers are considered structurally similar if and only if they have similar entry values and they share the same set of semantic strings and their placing order, and they share the same format of length fields, and they share the same encoding format, and they have similar length value. Before talking about signature generation, I would like to show you 2 sample signatures that our system produced. The name is machine generated. It is based on the pattern summary and creating time. The name is used for later identification. The ordinal is to tell the inspector engine which message should be inspected. For register message, it is a value of 0.5 and 1.0. It means the register message is the firstly exchanged message in the 0.5 round of C and C interaction. And the length value is to tell the inspecting engine which length the register should have. It is matched by this rule. And the entry value is used for reference for inspecting. And the pattern is easy to understand. It's just used to tell the inspector engine at which offset, how many and what contained bytes should exist. Signature generation. A set of signatures are generated for each group of structurally similar registers. The generation steps including finding out frequent items of offset and byte value, merging offset continuing items of offset and byte value, and normalizing them into valid signatures. And we define some policy for batch signature generation. The at least occurs means how many registers are needed to generate a valid signature. The least signature bytes means how many pattern bytes a valid signature should have. And the at least continuous signature bytes means how many multi-byte pattern as valid signature should have. A priori and IP growth is a classic data mining algorithm. We use them to find the frequent items offset and byte value. The wiki says a priori is an algorithm for frequent item set mining and association rule learning over transaction databases. And the FP growth algorithm solves the same problem but has better performance. And currently we use a priori, and we will soon update our system to IP growth for better performance. 3 types of signature are defined. The first is called normal. It just defines specific byte patterns occurring at a specified offset. The second is called PCIe. It is produced by replacing the semantics patterns with equivalent PCIe expressions. The third is called entropy. It is used when no valid patterns could be generated, and all the registers have the same length and very close entry values. We have implemented our idea in C++ and Python. Our solution contains about 2,500 lines of C++ code. Our test shows that it takes less than 30 minutes to classify 10,000 registers. This test is done on a machine have this configuration, and only a single thread program is used. We also did many tests to find the best choice of k value for k-means. As shown in the figure, the x-axis stands for k value, and the y-axis stands for the successfully classified number. Our test shows that 20 is the best choice for k-means. Positive negatives and false positives. We test our system with about 5,000 family known registers. The false negative is 3.91%, and the false positive is 0.3%. We also do some tests to see how many rounds are needed. Our test shows that when classifying less than 10,000 registers, 4 rounds is enough. And as you can see, most of registers are successfully classified in the first round. Here are some signatures that our system generated. These signatures all have large coverages. The first is for the classic stun. This protocol is used for net traverse. When we run unlabeled samples in our sandbox, we collect many registers of this kind. We have no idea whether it is malicious or not, and our system generates a signature for them. The second is for a kind of SSL client hello. In fact, we collect many kinds of SSL requests. They have different version value and substitute combination. The third is for a bot named Blood Bindi. Yes, you can see this bot has a text format register, and we currently have no idea what is the malicious purpose this bot has, but we are sure that this bot is malicious. The last is for the notorious DDoS bot Nito. This bot has a binary format, and its register message has operating system, CPU information, and memory size and net speed information. Of course, there is no perfect solution. Here are some pitfalls we think exist in our system. The first is not all botnet use registers in the C and C protocol. The second is for UDP-based C and C protocol, it's hard to tell which message is registered and which is not because of its stateless nature. The third is the same register may be shared across different C and C protocols. Further work need to for the right classification. And the last is our system is not good at classifying text format registers with non-fixed length. The final is conclusion. Our test shows that statistical and structural similarities among registers can be used to classify registers effectively, and register-based classification can complement C and C-based classification. And our solution performs better when dealing with binary format registers than text format. That's all. Any question? If you want to, okay, thank you. Thank you. If you want to further discussion, please feel free to contact me by this email or my Twitter account. Okay, thank you.
Well, do you have questions? Over there.
Thank you for the talk. To execute the binary, you actually have to defeat all the anti-forensics and so on. So do you have any advice or any insights on how to do that quickly and efficiently?
I'm sorry?
To actually get the register message, you have to get the malware to run. And that is difficult to do because of all the countermeasure inside the malware?
Yes, yes. Of course, there are many malwares that did not show their C and C behavior in our sandboxes. This is our future work.
Okay.
Yes.
And did you get any results with just the binary? Can you extract the register message just looking at the code without executing the malware?
No.
Okay.
Currently not.
Thanks.
Okay. Another question? No more. Okay, thank you.
Thank you.